You just watched a fluid swirl inside a box. Now let's build the solver that computed it. Line by line, no black boxes. Every CFD program you will ever write, from this cavity flow to a full aircraft simulation, has the same 5 phases. Define the domain. State the governing equations. Discretize them. Solve the resulting system. And post-process the answer. This map stays with us for the whole video. Whenever we move to a new phase, we come back here, so you always know exactly where you are. Phase 1. The domain. Let's start. Phase 1. The domain. Before any physics, we decide where the flow happens. A square cavity, 1 meter on each side, filled with fluid. 3 walls are fixed. The top wall, the lid, slides sideways at 1 meter per second and drags the fluid with it. We cover the box with a 41 by 41 grid. In code, the domain is just this: a box size, a grid resolution, and 2 arrays of zeros. Stream function and vorticity. Those 2 arrays are about to become the entire flow field. Phase 2. The governing equations. What laws does this flow obey? The full Navier-Stokes equations couple velocity and pressure. But in 2D, there's a beautiful shortcut. Rewrite everything in terms of a stream function, whose contours are the streamlines, and the vorticity, the local spin of the fluid. Pressure disappears entirely. 2 scalar equations. That's all. In the script, the equations live in comments. The code only needs their consequences. What we type are the parameters: a Reynolds number of 100, the lid speed, and a time step chosen for stability. Phase 3. Discretization. This is where calculus becomes arithmetic a computer can do. Every derivative becomes a stencil. The Laplacian is the 5-point average you'd expect. But walls need special care. Vorticity has no boundary condition of its own, so Tom's formula manufactures one from the stream function next to the wall. Watch the lid speed you appear in it. And here it is as comments the code will honor. Central differences for space, forward Euler for time, and Tom's formula to pin down the vorticity on the walls. That last one is where the lid actually enters the mathematics. Phase 4. The solver. 2 equations, 2 very different personalities, so we need 2 loops, one inside the other. The stream function equation has no time in it. The flow pattern adjusts instantly. The vorticity equation is all about time. Spin is carried and diffused. So, an inner loop that relaxes the pattern inside an outer loop that marches the spin. That nesting is the solver. Read it from the outside in. The outer loop marches vorticity forward in time. Each step, the inner loop relaxes the stream function to match. Velocities come from its slopes. Tom's formula repins the walls, and the transport equation moves the spin. When the field stops changing, the flow is steady, and we're done. Phase 5. Post-processing. A converged array of spin values means nothing to a human until we draw the streamlines. Before we plot, predict, the lid drags fluid right, walls turn it, so one big vortex fills the box. It's center-pulled up and toward the lid's motion, with tiny counter-rotating eddies trapped in the bottom corners. If the plot doesn't look like this, something is wrong. Stream plot draws the flow, colored by speed. And one print statement turns this from a pretty picture into science. Our vortex strength lands within 2% of the Ghia benchmark. The 1982 paper, every CFD code on Earth is tested against. In a moment, you'll watch that number appear on my real screen. 5 phases, 5 blocks of code. Watch them become one script. Domain. Governing equations. Discretization. Solver. Post-processing. Navier-Stokes solved in about 60 lines. Every one of them, you now understand. This exact file is what I'm about to run. Everything you just saw was the blueprint. Now, no mock-ups. Let's switch to my actual screen and run it for real. Domain, governing equations, discretization, solver, post-processing. That map is every CFD code you will ever write. Next episode, we keep the map and just swap the physics. The fully annotated cavity script, plus 7 more verified solvers and their derivation PDFs, is in the Flow from Scratch pack. Link below. Domain